Good morning. We are going to go over Chapter 5, Section 2 review questions 27, 28, 30, and 31. So if you will turn to page 135, we will get started. Okay, so first of all, you just had to understand the difference and the similarities between static friction and kinetic friction. So how are they similar and how do they differ? So first of all, static and kinetic friction both resist movement. Static friction, I like to think of it more in terms of inertia. It is what keeps an object still. And in order to overcome the inertia, you must overcome the force of static friction. And so your force has to be larger than the weight times the coefficient of friction, of static friction. So what about kinetic friction? Well, kinetic friction is a little bit different. It's the resistance to motion once an object is actually in motion. So yes, it's resisting, but remember, your object is still in motion. So that's kind of how they're similar and how they're different. So let's take a look at actually applying those kinds of ideas. So at a wedding reception, you notice a boy who looks like his mass is about 25 kilograms, because of course that's what you're doing at a wedding reception. And he's running across the dance floor, and then he slides on his knees until he stops. If the coefficient of kinetic friction between the boy's pants and the dance floor is 0.15, because remember, there are no units with the coefficient of friction, what is the friction force acting on him as he slides? Okay, well remember, the first thing we want to do is write down everything that we know. We know that the boy's mass is about 25 kilograms. We know that the coefficient of kinetic friction is 0.15. And we know the acceleration of gravity is negative 9.8 meters per second squared. But since we are solving for normal force, you can go ahead and leave 9.8 as a positive, okay? So let's set it up. So we have our normal force is going to be equal to 25 kilograms, that's the mass of the boy, times the opposite of gravity, 9.8 meters per second squared. So his weight, or the normal force acting on him, is 245 newtons. Like I said, we know that the mu of kinetic friction, or the coefficient of friction, is 0.15. So let's set up the whole problem now. The force of friction is equal to the coefficient of friction, right here, times normal force. That's the weight acting in the opposite direction. Well, that's 0.15 is your coefficient. We already calculated his weight, so it's 245 newtons, and you just multiply those two things together, and you should have gotten 37 newtons using significant figures. Okay? All right, let's go on to the next one. The coefficient of static friction between a 40 kilogram picnic table and the ground below that table is 0.43. How large is the greatest horizontal force that can be exerted on the table without moving the table? So first of all, if we're not in motion, we are solving for the force of static friction. Okay, so let's see how we're going to do that. So we know that the coefficient of static friction was given to us, and it's 0.43. Excuse me. The mass of the picnic table is 40 kilograms. You also know that the acceleration of gravity, I probably should have written an A there because we want to do the opposite of gravity, is 9.8 meters per second squared. So we just leave off the negative. We also know that the force of static friction is less than or equal to the coefficient of static friction times normal force. Remember, this one is your weight in the opposite direction. So let's solve for weight first, or normal force. You know what I'm talking about. Okay, so we have 40 kilograms times the acceleration of gravity in the positive direction, 9.8 meters per second squared. And that gives us the normal force acting on the picnic table is 392 newtons. All right, so that's part of ours. Now we know that the force of static friction is going to be less than or equal to, what was our coefficient? 0.43 times the normal force, or the weight, in the opposite direction, 392 newtons. That gives us an answer of 169 newtons, making sure that you are using 3 significant figures. So you might ask, well, wait a minute. Gravity only has 2 sig figs, 9.8. Well, we are using this to calculate. It was not given to us in the problem, correct? So we have to use whatever is given to us in the problem. Well, this one only has 2 significant figures, so I guess I could have just left it at 390 newtons. I'm sorry. Down here, I could have left it at 170 newtons. Ignore what I just said. Because you only want to round your sig figs at the very end of your problem. So 170 instead of 169 newtons. Let's look at our final problem. And I will tell you right now that the final problem, well, you'll see. I drew a little picture to represent it. Oh my Lanta, so many forces. Oh, this one will about drive you batty. So let's get started. You push a 13 kilogram table in the cafeteria with a horizontal force of 20 newtons, but the table doesn't move. So right away you know that the static force is going to be greater than what you're pushing with because you can't budge it. Then you push the table with a horizontal force of 25 newtons. Now it's moving and it accelerates at 0.26 meters per second squared. What, if anything, can you conclude about the coefficients of static and kinetic friction? Well, the first thing you need to realize is that there are an awful lot of forces going on here. So we're going to break some things down. Because the force of friction, we're going to need the force on the table minus the force with which it's moving. So I'm going to substitute. We know that force of friction, if I wrote it out, is actually the coefficient of kinetic friction times normal force, right? So instead of writing this, I'm going to substitute the actual formula. So bear with me. Now this is going to equal my applied force to the table minus the weight of the table, because I've got these 2 forces that I have to contend with. So, I'm sorry. This is my applied force. This is not the weight of the table. I apologize, I misspoke. This is the horizontal force causing the acceleration of 0.2 meters per second squared. Ignore me, please, when I said weight. That's not correct. Keep following me. The way I've set it up is correct. The way I worded that originally was not correct. This is how much force you're applying. This is the mass times the acceleration horizontally, okay? So we have to subtract this. So here's my applied force, the 25 newtons. Now I'm going to subtract my horizontal force. That's the mass of the table times the acceleration on the horizontal axis. And I want to get my coefficient of kinetic friction by itself. So what is normal force? It is the opposite of weight. I have to divide by the weight of the table. I know, that's a big one. So let's see. If I do this calculation on top first, I come up with 21.62 newtons. And that's my applied force of 25 minus my horizontal force, the 13 times 0.26, and that'll give me 21.62 newtons. I'm going to divide it by the weight, and the weight is 13 kilograms times the opposite of gravity, 9.8. So my normal force, or the opposite of weight, is 127.4 newtons. If I divide these two numbers, these two forces, I will then get the mu of kinetic friction, or the coefficient of kinetic friction, which is 0.17. You notice that our units cancel out, and there are no units on the coefficient of kinetic friction. So we can solve for that. What do we know about the static friction? Well, we don't. We could calculate a range for it. I'm not going to ask you to do that. I would expect you to be able to come up with the coefficient of kinetic friction because we are given everything to solve with it. However, to solve for the coefficient of static friction, we would have to go back and instead of using the applied force and this, we would have to go back and just do the applied force, the applied force on top. Remember that was 20. They used 20 newtons and they couldn't move it, could they? And then I would divide that by the normal force acting on the table, basically the positive weight of 27.4. And this would give me a start for my static friction. I don't know what it would be equal to though, right? Because at 20 newtons, I couldn't move it. So I know that it's somewhere between the fact that I couldn't move it at 20 newtons and I'm actually having an acceleration at 25 newtons. So you know that we could probably find a range for that. I am going to stop there. I think that's a good 14 minutes for you guys, or almost 14 minutes for you guys for physics. There is no homework over the weekend. However, on Monday, I expect everybody to attend the Zoom, and we are going to get started on the last part of this chapter. Have a good weekend, everybody. Bye-bye.